Welcome back to the course on architectural design of ICs. Okay, so this is the third lecture on introduction. So, yesterday we have seen this in the, that means if FPGA design style, it has to start with specification, then you have to, that means the RTL specification or detail design, then function simulation, and then synthesis, then timing simulation, and then you can go for the device programming part. So, and what I said that this logic synthesis is the part for converting from the logical expression to the gate level netlist. Okay. So, just more onto this, what does it mean this logic synthesis, just more add to on that particular perspective. It has to start with this Wedge-Del or Verilog. Okay. Then the synthesis procedure that or this process that basically converts this Wedge-Del description to implementation technology specific primitives, like in for FPGA it has to be implemented using lookup tables, flip flops or RAM blocks. In ASIC it has to be that means converted into the corresponding standard cell gates or flip flop libraries or memory blocks if it is available. Okay. So, that means you have this particular information in your library. So, those particular whatever logical expression you are describing using the HDL language during the synthesis, that will those gates or those operators or those memories will be called to implement your particular system or the particular expression which you have mentioned in the EDA tool. Okay. So, that is the process for logic synthesis. Okay. So, then why do I need to do this synthesis? So, it automatically this synthesis process is basically automatically manage many details of the design process. It reduce the number of bugs. Bugs means that means the fault you have in your system. Okay. And this also improve the productivity. Productivity means so synthesis once you done, if you that means the performance wise it will be much more on the higher side. Then this abstract design data from any particular implementation technology in many cases leads to a more optimal design than could be achieved by manual means. That means this this is all about this automatic or this tool based synthesis process, and apart from this, that means synthesis process means it has to pass through this optimization phase as you are putting the constant to it. Okay. To the tool, but manually optimization sometimes you can do the mistake. Okay. So, that is why automated tool wise synthesis optimization is sometimes it is better, but whenever you are doing this automated synthesis at that time very much you have to be very much careful, because the synthesized hardware does not meet the specification. Whenever this particular circumstance happens, so at that time you have to be more careful. How you have to be more careful? You have to be more, you will be knowing that it is not meeting the specification after, that means doing the simulation, or sometimes what happens during the optimization, tool based optimization, sometimes this this logic representation that changes. Okay. So, to check all these things you have to be more cautious about doing this automated synthesis, though we will learn more on this manual optimization. Tool also do the optimization. So, both the things you have to know. Okay. So, whenever you are following or we are using this tool based optimization, so at that time on the background some of these are already running. Okay. So, as a designer or as a researcher, I have to know both the things, that means the manual optimization. If I know the manual optimization on the background, what is happening, how it is basically the tool is doing the optimization, that also will be very much known to me. So, this architecture definition. So, this course is all about this architectural designs of ICs. The first thing is that architecture definition. So, what does it means? Okay. So, this you have to build one system. So, at that time the design will be for a larger design, it has to be partitioned into two architecture. You can just partition it, one macro architecture and another is the micro architecture. So, what is that? It is a method, this design partitioning is a method which will be used to divide the design into smaller functional element, so that a very complex design is split into simpler and inner level modules. That means, it is that means if I that means just work on a very big complex circuit. So, it will take me to verify or to describe that particular system, it will take too much of time. So, instead of that, if I split that particular blocks into several chunks and each of these chunks will be monitored, or as a designer you can monitor each of these things very easily, and once each of these chunks or each of these blocks or these sub blocks under the main blocks, each of these sub blocks are verified correctly, at that time you just integrate them all in all and you build a particular main module or the main block. Okay. So, then what is the need for partitioning? So, here the idea is that divide and conquer rule. Okay. So, instead of doing the whole thing at a time simultaneously, you just divide the things into several blocks and do it parallelly. Okay. So, that means the time also for building the particular blocks, the time also I can enhance by simultaneously doing the sub blocks, and separate distinct functional blocks, focused verification efforts, reuse of a module across various designs and projects, workable size of a design for a set of tools, parallelizing work among team members, need to meet physical design challenges and constraints. So, you see there are several several advantages of doing the partitioning. So, the verification that becomes easier, okay. And suppose one block is used for different other application too, or for, so if I block wise, if I just divide it and that particular block, that will be used many of the system if it is required. Okay. So, once you develop, you use it for different application where it is required. Okay. So, that means, and as I said that the partitioning basically it helps to parallelizes your work. So, obviously, it reduces the design time. So, what I said that okay, that this is this ASIC design flow. So, in ASIC design flow, this floor planning, placement, then this clock tree synthesis, routing, and then for this send it to the fabrication lab. So, this back end part, this part is basically changes from the FPGA design flow. This front end part or this the specification, then this architectural definition, then this synthesis, then simulation, then timing analysis, all this part is basically common in both of the case, both of the design style, but this portion, this device programming or in ASIC design, this has to be do it manually, where you are getting that thing in ready made there in FPGA design style. So, this is just one example of one complete placed and routed chip under the, that means if I follow this ASIC design style. So, this is the, that means I am talking about this layout. So, what is this layout is nothing but this physical that means view of the corresponding circuit. So, suppose this is one, this transistor level that means schematic of one inverter, and this is the physical description of that particular inverter. Okay. So, here this particular things is basically related to PMOS and this particular things is basically related to NMOS, and then there is the connection, as there is a connection common between these gates, and then this is this for the out there is a common source, and from there there is a out. So, this information this for PMOS and for NMOS, this information is very much common, or this information will be provided by the technology library which you are using. Okay. So, this will be different for different vendors. Okay. So, you use those that means information for particular vendors, and you have to, after this, that means the whole, suppose this inverter circuit I have built. So, this particular geometrical description file, that will be sent to the corresponding vendors only. It is not that the vendors like TSMCs are there or UMCs are there, some of the, that means companies are already there. So, if I use TSMC, one particular that means vendors this information, I cannot send it to the other vendors for the fabrication. Okay. So, otherwise it will be it will be, that means not recognizable by their manufacturing process. So, that means this is the process of device fabrication. I will not go details about this. That means once this geometrical that means files has to be sent to the fabrication. So, then this fabricating lab or this fabrication lab, they has to follows through the device fabrication procedure, and they after that they build the corresponding system for me. So, this logic synthesis is that here is this VHDL code which I have that means this is the logical expression which I have written using VHDL language, and this is the corresponding gate level netlist or the circuit level implementation of the corresponding circuit which what I have described using VHDL. So, after that, before to start with these things, we are basically very much cautious consider about this. In any VLSI design style, there are three things you must have to be consider, that is speed, power and area. So, these three are the major concern in any system design or VLSI system design. So, whenever we are talking about speed, at that time this critical path comes. So, these are the basic things which you have to know from the beginning, because we will use these things in the later on. So, what is this critical path? The definition of the critical path is that this is the longest path from the outputs of the register to the input of the registers. Means what? Suppose this is one registers, this is one registers, and inside of this register there are some this combinational circuit, or it has to pass some of the logic gates. Okay. So, this is that means the critical path is that the input of the register, this input of the register to the output of the registers. Okay. So, what does it follows? This T critical is then follows T flip flop plus this is the T logic or the delay for this logic gates, and then this is the T flip flop setup time. Okay. So, why I need to consider this the delay about this T flip flop setup, and then this T flip flop of this particular circuit we will come to the later slide. Okay. So, once you got the critical path, okay, so the minimum clock period is the length of the critical path, and then the maximum achievable clock frequency equals to 1 by this minimum clock period. So, this is the definition of maximum clock frequency, and this is the definition of the critical path. So, then another information, that means another important part of this is that clock jitter. So, it happens that we consider, or we for a synchronous design, we consider that each of the system will be work on a particular edge of the clock. Okay. So, it is not that only rising edge or the falling edge also, but it has to occurs, or it has to work on the edge of the clock. Okay. So, it is whenever the clock has been that means generated. So, at that time it is not that all the edges of the clock occurs or at the same time. That means, this particular edge is not at all precise for all the clock edge occurs for a that means ongoing clock. Okay. So, that is why what happens, it may cause faults in the circuit. So, that is why whenever we are using one clock source, at that time we have to be more cautious about this jitter free clock for the proper work of the system. So, then another important parameter is that clock skew. So, clock skew is that the rising edge of the clock does not arrive at clock inputs of all flip flops at the same times. Means what? That means rising edge of the clock does not arrive at clock inputs of all flip flops at the same time. When this type of that means scenario happens, here you see this clock is applied in this particular first flip flop, then second flip flop with some delay. So, delay means if I use gated clock in any of the flip flops, so at that time the clock which is basically applied directly and the clock which is applied after delaying or after using some gated logic. So, there will be a difference of arrival of the clock edge to those particular flip flops. So, at that time this clock skew occurs. Okay. So, as you can see that there are these two, basically these two flip flops are connected via some logic. So, and the clocks are basically also differs, the arrival of the clock is also differs. So, this may create some problem to the system. Okay. So, then another thing is that the static timing analysis. So, here you see this is one particular circuit. Okay, just we will consider that thing in later. So, then in another two things are there, which is that false path and multi-cycle path. False path is that very slow signal like reset, then test module enable that are not used under normal condition are classified as false path. And what are this what is this multi-cycle path? Paths that make take more than one clock cycle are known as multi-cycle path, and it has to define the multi-cycle path in the analyzer, and it takes those constants into account when synthesizing. So, what is the meaning of this? Multi-cycle path means, suppose here I am having this this flip flop, these two flip flops that are basically connected, in between of that there is one multiplier. This multiplier takes 5 clock cycle. Okay. So, that is why that means the data transfer from these to that I have to wait for 5 clock cycles here to that means to properly arrive the data here. Okay. So, that is why this particular path is known as multi-cycle path. Whenever I am doing the synthesis, at that time I have to mention that okay, this multi-cycle path is from this Q1 output to the this D2 input with multi-cycle of 5. Okay. So, that we have to mention, and this is in this if you use synopsis tool set, this is the command for to do that. Okay. So, as I say that there is a that means very much that means relation between the speed, power, any area, these three are the major constant or the main constant in your VLSI system design. So, another thing is that is the testability. So, each of these that means each of these 4 area, speed, power and testability, each of these are basically interconnected to each other and they have trade off among them. So, why they have trade offs among them? That means it is not that I can achieve the speed and area both at a time. Okay, for on the that means in the linearly I can increase speed and area both. Okay, because they have the trade off. Either you can go for the speed, if you increase the speed, so at that time you have to be lose the area, or if you just reduce the area, so at that time you have to lose the speed. Okay. But in area and power, if you reduce the area, so at that time obviously you can save the power, and speed wise also if you increase the speed, obviously you will that means require more of the power. And for testability options, so for it is not that what I say this time to pressure, the time to market pressure, that are that becomes very much important nowadays. So that initially whenever you have designed the system, at that time the test option you have to, from the beginning you have to put that test option to the circuit itself. Okay. So, the after fabrication, the testing of the particular chip, that becomes very much easier. Okay. So, whenever you are putting the additional test logic to your system for building or to make one fault free or bug free chip, so at that time obviously you are putting or you are that means compromising with speed, power and area. So, that means their testability is also basically there is a trade off between this speed, power and area. Okay. So, that is why there is all these 4 are connected to each other. So, what as I said that whenever there is that means if you try to increase the, that means if you try to decrease the area, so at that time you have to lose in terms of speed. So, speed can be in terms of latency or in terms of throughput, and if you just increase the speed, at that time you have to put the parallelism here. Okay. So, at that time parallelism means more of the, that means you can make multiple copies of that each of the processing element and you can process it simultaneously. So, that means each of the processing elements you are copying means more the number of processing elements you are copying or you are putting to do the same work to finish your job early. So, that means you are increasing the area. Okay. So, then this is not at all. So, some of the, that means whenever we are doing this particular synthesis procedure, so at that time some of the things you have to be avoid. You have to be avoid this this hierarchical combinational blocks, like here if you see I have this register 1 and register 2, among them I have 3 blocks, this is block 1, this is block 2, this is block 3. So, the path between range 1 and range 2 is divided between 3 different blocks. Due to hierarchical boundaries, optimization of the combinational logic cannot be achieved. So, synthesis tool maintain the integrity of the IO ports and combinational optimization cannot be achieved between blocks. So, that means instead of putting different sub blocks or this sub combinational block inside in between this register to register connection, you put it into, you club it into a that means common combinational logic, where the synthesis tool can easily apply the optimization procedure and it can gives you a better result. So, it has to, that means as a designer you have to avoid this type of hierarchical combinational logic if you are following this type of particular system design. And the how to handle the combinational path. Okay. So, if you just see another logic, that means the two registers it has. So, combine all the logic 1, logic 2, logic 3 level into one system, and this is the block A and this is the block B. So, here you see this is block A, this is block B and then block C. Instead of that, you just put it this one as a block A and this one as block B or block C. So, here you see all the combinational circuit is grouped in the same block that has its output connected the destination flip flops. It allows optimal minimization of the combinational logic during synthesis and allows the designer to simplify description of the timing interface. Okay. So, or else what you can do, that means if I am having this kind of that means combinational logic. So, then I can put the registers here after each of the combination logic I can put the registers, and so that means what does it means, or this will basically avoid the problems which occurs during the synthesis, automated synthesis. Okay. So, for today this is it. Okay. So, next day in next lecture we will see some of the example. Okay. So, how we can apply our that means tweak or some of the that means tricks to get that, suppose one specification is I have to meet. So, an algorithm is fixed or the algorithm has been developed by the designer. Okay. So, as a architectural design, how I can use some of the tricks to make or to meet the specification in a easier way. Okay. So, that we will see in the upcoming that means lectures. Okay. So, for today this is it. Thank you.